Speaker lineup. Without further ado, let's give a round of applause to Gastón, who's going to take us through practical usage of CAP theorem.
Okay, thank you. Thank you, everyone. I'm really glad being here. As Amit told, I was part of Glovo before, so I'm really happy to be here sharing the stage with Fanta and Pablo, who are awesome engineers. I'm really happy to be with them. So first of all, why this talk? This is probably most of you heard about the CAP theorem. If you don't, probably you will learn something today. But when I first started learning about CAP, I heard consistency and I get confused with acid consistency. And I thought at that time, I didn't understand it properly. I thought, okay, this is easy. I understand how it works. But then, after 15 years, now I know I knew nothing back then, and I want to share some examples so you can also get a better understanding of CAP. Who I am, Amit already did a great job introducing myself. This is a photo thanks to my former colleague, Mauro, my friend. He took it in one of the offsites, and then Nicole presented it in one of the Glovo All Hands while I wasn't here. So it's a little bit of an internal joke. I worked in the past in Argentina for Despegar. I worked 1.5 years at Amazon, and I spent like 3 years at Glovo, where I get to meet a lot of amazing engineers. Now I'm working at Unleash, which is a feature toggle open source system. And I work with multiple languages, DevOps. I'm really customer obsessed. This is something that sticks with me from Amazon. On the agenda, we're going to do a quick recap just to make sure that we are all in the same page. Then we are going to look briefly at how to design CP and AP systems. Just for reference, CAP is consistency, availability, and partition tolerance. And the last part, I think the most important one, the main takeaway, how we used these concepts to build some features in Unleash. Okay, first of all, what is CAP theorem? Basically, from these 3 properties of any distributed system, you can only pick 2. And we will go into details of each one, and hopefully you will get to understand why you can only pick 2. So to get started, let's try to understand what a partition is, what a network partition is. Imagine you have this distributed system. You are trying to write something in one server. Imagine this system as a black box, and then you want to read from the system, eventually from a different node. The idea is that you should get the value 3 after you wrote x equals 3. But it may happen that this connection or this link between the 2 nodes is broken temporarily, hopefully. And in this situation, when you try to read x from the other server, you need to decide what to do. So what options do you have? You cannot magically transfer the information from one node to the other if those nodes are disconnected. So the choices you have is you return whatever you have in the local state of that server, making you available, or you say, sorry, I don't know how to respond to this request, so I'm going to fail. Come back later, and try again. Partitions will happen in any distributed system. If we remove the distribution, probably it's not a problem, but even if you only have one node, you still have to connect to the node via some network, unless you are connecting via wire. And being partition tolerant means that if a partition happens, your system will continue to live. Not being partition tolerant means that you cannot survive a network partition. And that's probably not something you want, because you know that partitions will happen. For any distributed system, if you want to give a partition tolerance, and this is something that Google tried to prove that they don't lose packages in their network, you basically need to have a network, a fully reliable network where you never lose a package. The package is never delayed. And that, unfortunately, it doesn't happen. Okay, I went too far. Okay, so now we know, and we briefly spoke about what can you do when you have a partition. One option is being consistent. If you're being consistent, you somehow need to know that there is a network partition, and then you can say, hey, sorry, I have a network partition. I don't know if I will give you the right response, so I can fail, and you can retry later, and that is okay. The idea is that all clients should see the same data all the time, no matter to which node you connect. And here, a special note about consistency, the other consistency from ACID. Don't get confused, as I did in the past, because I was struggling with these two concepts. Consistency is not the same as consistency. Consistency in ACID, it means about conserving the state, a valid state in the database, right? You start one transaction, you commit the transaction, and you move the database from one valid state to another valid state. Consistency in CAP means no matter which node you read, you will get the same data. Okay, you can get confused, try to think about it, but it's not the same. Consistency is also used in a third context, but let's keep these two for now. Okay, so we said if we want to be consistent, we can either fail if we identify a network partition, but if we want to be available, because by some reason you need to send the response, you can return whatever data you had in the system before. The idea is, depends on the system, on what you're working on. You may want to be consistent or you may want to be available. If you are developing some social network like Facebook, this is the most common example. If you suddenly don't get that two other persons give a thumbs up or a like to your post, it doesn't matter. You can just reload the page and you will get it. So it doesn't matter that much to trade consistency in this kind of system. But if you are in a bank, probably you don't want to give up consistency. Okay, very briefly, how do you design a consistent system? First, you start with a problem. If you start with a single node, this is a single point of failure. If this goes down, your system goes down. So in any distributed system, you start by trying to build a redundancy. So you want to have multiple instances of your server. You want to have multiple instances of your database. Now, how do you make this database consistent? This is a challenge. We said that to be consistent, you need to return the same data no matter which database you are connecting to. So one of the ideas is you can simply, whenever someone is writing, like you're writing x equals 3, you can wait until you have an acknowledge from every node in the system. Whenever you got that confirmation, you can send an OK to the customer saying, yeah, this is OK, we accepted your write. But as you can imagine, this will take a little bit of time. So there are other solutions, like you can use quorum when you're writing. So you write to the majority, and then when you read to the majority. Here you are sacrificing a little bit of latency on the read side to have more or faster writes, sorry. But I'll go down into some example. Again, this is one way. There are multiple ways, but just the idea of this talk is to give you an understanding of these concepts, just that. And let's look at an available system. Again, we start with the same. We have a single point of failure. We want to have redundancy. And in this case, I'm going to be presenting a different example. Sorry, I think I skipped. Okay, no. It's okay, it's getting there. I'm presenting a different example. Again, if in the previous example, we said we are writing to 3 nodes. Imagine that you say, I want to be available. I'm going to return whatever data I have in the database. I write to one node because I want to be fast. And then I read from any node and I return the value that I have. One day or 1 minute, you are going to get bananas. The other minute, you are going to get apples. You are going to get a 3, a 4. It's going to be random. So you don't want to just be available. You also want to have some consistency. So it's not always A or C. CQRS is an example where you can have and build a highly available system without having to trade a lot of inconsistency. You basically have a write model, which is consistent. Again, here is a simple database, but probably you also want to scale this and have replicas and such. But this is a consistent model. And then you have some process that will prepare your data for reading, basically to optimize the way you want to present this data. This means that eventually you write something to a system and eventually you will get the response that you wrote. But if you are too fast, you will probably get stale data. And that's okay, because here we are trying to be available. We are not trying to be consistent, okay? So that's more or less to get a high-level overview of how to design consistent or available systems. I hope you got the idea, but we are going to touch in some more details later. Now I want to explain what feature toggles are. So again, we are all in the same page. The simplest explanation, sorry, if I'm in the middle of the screen, please let me know, because I don't know where to stand. It's an if statement, okay? But this if statement is special because it's controlled externally. It's not from the same system that it's running this code, it's from an external system. The benefit of this is that you can have an external person modifying the features, this other system, and with this is changing how your system behaves. This means that you can have changes in your production system without having to deploy anything. Someone can control if there is some issue with, I don't know, new behavior, you can roll back by just changing some configuration there. So in this particular system, the question is, should we prioritize availability or consistency? What do we do? Do we choose one or the other? It's not that simple, as I tried to explain before. So I'm going to introduce a new theorem, which is called PACL, or at least that's how I heard it in YouTube. The idea is that the cap theorem is limited to partitions. Whenever there is a network partition, what do? Do you choose availability or consistency? But in most of the cases, 99% of the times, your system will not have a partition. So what do? Are you fully consistent? What are you trading if you want to be fully consistent? You are trading on latency. And this is where it becomes a little bit more interesting. It gives you a spectrum. And here I'm using MongoDB, but the example is more or less the same that I presented before. You can write to one node. And if you write to one node and then read from any, 1 out of 3 times you will get the right response. So you can have a very low latency on the reads and on the writes, but you are trading on consistency. If your system can handle this on your end, then that's fine. But most of the times you will try to be more consistent. So you can use quorum, or this is right concern majority. And then when you read, again, you can still read from only one node. And 2 out of 3 times you will get the right response. Or you can also use the same thing for reading. You can use the read concern majority, and then you can disambiguate. You can, if you get 2 number 3s from 2 nodes and 1 number 4 from another node, you know that you need to show the 3 because it's the majority. But you don't need to wait to all of them. As long as you get n plus 1, n being the half of the nodes, you can return that value. Or the other option is you can be fully consistent, but you are trading more latency. And it gets more complex again, but this is just to give you an overview. I don't want to go into these details. There is a cool site called Shepsen where all of these concepts are explained. So consistency has different layers or properties. And the idea is that each one of them compromises others. If you see the top ones, which are in this pink color, these are the most consistent ones. But the problem is when you are consistent in the situation of a network partition, you cannot be available. You have to give up availability. There is a middle ground, which is these orange ones, that if you have stickiness in your connection, that means if you write to one node and only read from that node, you will get the value and you can still be available. But if you don't have stickiness, you cannot be available or you will be inconsistent. And then this last one, the light blue ones, in this case, you can be available, but you are giving up a lot of properties of a consistent system. I don't want to go into detail. This site is really cool. I highly recommend it. They test a lot of databases that probably you are using in production, thinking this is excellent, this is consistent, and they break it down and say it's not like that, or they help fix bugs. It's really cool, but it's too technical for this talk. Okay, another concept is eventual consistency, which more or less comes from these ideas that I was sharing. The idea is when you are writing to one node, you want to replicate this data to other nodes. That takes time. So eventually, if you are reading here, you need to wait the data to propagate. But you don't wait, when you are writing, you don't wait for a confirmation that it got propagated, because that node can be in another region in the other side of the world. You don't want to wait a write until every single node confirms. It's much easier to scale reads, and this is one of the reasons to use eventual consistency, because you can add more replicas. The only thing that you are trading is that it's going to take longer to have the data in these nodes over there. And here is where Unleashed takes a decision. When you are speaking about features, most of the times you can also think, oh, I can use this for configuration. And it's true, you can use feature toggles for configuration. But configuration, it's a little bit different because you read that configuration when you are starting your application, and probably you never read it again. And if you need to change a value, you probably need to reboot your application. So this is, configurations is basically like have few reads. You don't read that frequently. But when you are doing experiments or feature toggles, you're probably having a UI and you want to check on every single access to that UI, probably million of times or thousand of times per second, if you need to show the blue button or the green button, okay? So we are making a conscious decision that we want to have a highly available system. We are trading consistency just to have a very fast, again, reducing latency system that can scale massively. So if you remember the system that I described, how do you measure consistency? And please tell me how am I doing with time? Okay. How do we improve consistency? Availability. We have the feature toggle system over there. Eventually, we will have a network if you are using as a service, okay? So you would like to cache data here. But the problem is you have this context that you need over there to evaluate the state of the toggle. So the cache here is probably going to be ineffective. It is going to have a lot of misses and probably won't work. I wouldn't recommend do that. But, sorry, I went a bit too far. The idea is if we look inside, what this component is doing is just getting all, again, here we are in the feature toggle system. You get all the configuration, basically all that values that people set in the database, and you get the context, and you just magically say, okay, this toggle should be true for this context or false for this context. The good thing about this is that that database doesn't change frequently. This is from our data. We have an average of 10 updates per day per customer, an average. We have customers with more updates. And this data here can be easily cached, right? We can just store the values in a cache, refresh it frequently, and this system will have zero I/O. It will have everything in memory and will be really, really fast. How can we use that to improve privacy? If you look at this system, there is a problem. We are sending customer data. This data can be the email, bank account. I hope nobody does that, but any personal identifiable information. So we said, if we can cache this value, can we move this cache closer to a client? Can we move it like to the servers that the clients are running? Of course, you don't want to do this in the browser. So as we said, we are sending the context. We can evaluate really fast if the feature toggle, and that API call transforms into just a read only. We will read. Okay, yeah, I try to move. We will read from that database, which makes it much easier to scale. So the idea is Unleash consciously trades consistency to have a highly available system that can even withstand server outages, because if that system goes down, this part here can continue working. And this is one of the biggest values. Of course, if this node here goes down, then you need to store the state somewhere to continue being available, but that's another story. I'm not going to go into that, but it's possible. It also has a very low latency and high throughput. There's basically no I/O involved when you are you moving? When you are, I'm not moving, but okay, now it's working. You can horizontally scale the reads by just adding more computing resources, because this is basically CPU heavy. You just load everything in memory, that memory rarely change, and you evaluate a lot of requests per second. And the bonus, and this is the important part, we managed to use this to improve privacy. Privacy was not something that we had in mind when this was built, but it's something that is now rooted in the system. You can trust that your data will never leave your data center. And again, as everything in CAP and Parcel is a trade-off, these benefits don't come for free. Like monitoring is really complex, because now you need to monitor external systems. When some customer complains that they don't get the latest value, you basically have no eyes and you cannot tell what's going on if they don't share information. We need to support multiple backends, because this server here can be running in Rust, can be running in Python, in TypeScript, whatever. And that means that we need to support a lot of languages. That's a problem. And we also have additional complexity, because now this is running on the clients. And if they never update, and my Glovo folks will know that people usually don't update applications, this will become a liability for us. We have solutions around these problems, like having specifications which states how the server or how the SDK or this component here should behave under certain state and with certain context, so you can build your own SDK. And we also provide deployable artifacts in case you don't have a server. As I said, you don't want to drop this into the browser. We provide some Docker instances so you can run a read replica of Unleash in your server, in your network. So some closing remarks. Am I okay with time? Yes. It is important to understand your application to be able to use CAP effectively. We saw how feature toggles is a read-heavy application, and basically you are matching two contexts. So it's pure CPU that you are using. And understanding that lets you make the right decisions. And the other cool takeaway, I think this is one that struck me is that privacy was built in thanks to understanding these concepts, right? If we didn't understand the concepts, probably we would be sending data to the upstream server and caching some data locally. But we understood that we wanted to have something available and have this built in the service. So the idea is understanding this is important for you to see how you can contribute to your business, to whatever system you're working on, because you can build new cool features. And that's the last part. There are a number of references here, some cool videos, and the Shepsen site, I think, as well. And this concludes the first part of the presentation. Thank you very much. And now, my two friends. Enjoy.
I'll stay on this side. I apologize for my t-shirt. It wasn't meant for this meeting. It was another meeting, but I'm happy to be here. So I'll try to do my best. So the talk is gonna be our Glovo's journey of a migration from Kinesis to Kafka, and we're gonna start. Okay, this is the agenda. We talk about a little bit how Kinesis was used at Glovo and what we tried to improve Kinesis because we had some of the issues, and how we actually chose at the end to use Confluent Kafka, and all the journey related to the migration, and finally all the mistakes we made and the lessons we learned. Okay.
Okay, let's start. So at the beginning, I'm gonna describe what we had before with Kinesis and the way that we used to work with that. There are some terms here that I'm gonna use interchange during the talk, like in this case, for example, streams and topics, because for example, in Kinesis, we call them streams, while in Kafka, we call them topics. It's similar for partitions. In Kafka, we call partitions, and in Kinesis, shards. And in the case of the consumer group, we use consumer group for Kafka and application for Kinesis. But in the end, we are talking about the same thing. So this is an example of a stream or topic that we have in Glovo, which is called orders, and we produce multiple events from different types on the stream. And then we have multiple consumer groups or applications which are listening to those events. And for each one of these consumer groups, we can have one or more listeners or consumers, because in some cases we want to deliver the same event to multiple listeners, or we want to deliver different types of events, like in this case, for example, we use one consumer group and we deliver the order create to one consumer, which is basically a client code that will execute based on the event. And then we do the same for the deliver. So this is more or less what we had before with Kinesis, and we are still using the same approach, but with Kafka. So now let's talk about the limitations that we face with Kinesis. So I said before that we have this concept of shards or partitions. Basically, for every stream or topic, we can have one or more shards or partitions, which are used to process in parallel the events or the messages that we send. So in this case, Kinesis works with exposing an API per shard. And one of the actions that you can invoke in this API, it's called get records. So basically, it's a polling based system. You call this get records API, and you get a bunch of records and you process that information. The limit is basically in the number of times that you can call these get records in a second. So the limit is it's a hard limit of 5 operations per second per shard. So this is it's a problem, because basically if you have more than 4 consumer groups you will hit this limit, because for each one, you need to read for all the partitions. So at the beginning, we were using this approach without problems because we shared this consumer group among all the listeners. But then when we started to do more like specialization and like separate the consumer groups depending on criticity and other categories, we start like facing this issue. The problem is that when you exceed the limit, you get throttled by the Amazon API, the AWS API, and then you have to retry. So in the end, you will consume the events, but not at the speed that you might need to consume, because you need to retry sometimes many times until you get the actual value. So this, in some cases, is not a problem because we don't have many consumers, but for the orders topic, for example, in this example, at some point we had like around 50 different consumers from different applications, and we were hitting this limit like pretty hard. So this introduced an extra delay on the messages that we were delivering, and it was the main problem or the main limitation that we faced. It's important to mention that this is it's a basically limitation in the control plane API, because you have multiple limitations in Kinesis, and most of them are based on the throughput that you can move to produce or consume. But in this case, it's the number of operations that you can do. So it doesn't matter if you do get records and you get one element or you get 1,000, it's always the same. You have this hard limit of 5 operations. So when we discover this issue, we start thinking about improvements, because in the end, everything was running with Kinesis, and we want to stick that and do the improvements needed and continue using the platform. So we analyzed 3 options. We ended up implementing the first 2, and the third one was discarded because it's not I mean, something that we can sustain in the long term. So the first one is priority per application. So basically, since we are polling, we are calling this get records API. A way to avoid this limitation is to introduce a delay between get records, is to reduce the frequency that we use to poll. So we implemented this approach of priority, which basically was divided in 3 groups, medium, low, and high. So for low and medium, we basically defined some waiting time between the polling operations. In this case, I think it was 15 seconds for low and 5 seconds for medium. So basically, we were waiting that amount of time before doing the next get the records operation. But then we had some cases where the delays were not allowed because we wanted to deliver the messages as soon as we can. So we created this high priority profile, which is based on something called EFO consumers, which is an enhanced fan-out consumers. Basically, this is something provided by Kinesis, where you can have a replica of the shards to provide direct access to an application. So if you have, for example, you have a stream with, let's say, 2 shards, and then you want to enable this enhanced fan-out, you can create one consumer, which 2 separate shards which are only available for that consumer. So basically, you get the full throughput available for the shards for one consumer only. And that means that you get also the 5 polling per second operations per application. The problem is that you can create up to 20 EFO consumers per stream. This is also a hard limit in AWS. Sorry. And then another issue is that you have to pay separately, because in the end, you are creating more shards internally. You are replicating or duplicating the shards. So you have to pay, if you have one, let's say, stream with 2 shards and you have 1 EFO consumer, you have to pay for 4 shards, because in the end, you are replicating the value. So this is something that we implemented to initially to buy some time until we decide move forward with a full replacement. Then the second approach that we used was stream specialization, which is basically, in some cases, we try to instead of using one stream to put all the events types, we decide to split that in multiple streams, which are specialized to a specific operation. So if we do that, basically we are reducing the amount of operations that we are going to do per shard, because we have this now divided between streams. So we use this approach in some cases where it was available. Yeah. Okay, sorry. But this is not always possible because at some point we need to maintain, or we want to keep order in between the events, and we need to basically produce all of them in the same stream or topic. But in some cases we managed to basically split these to buy some time also. And the third approach is something that we did implemented. It was suggested by the service team in AWS. Basically the folks that are working on Kinesis, developing Kinesis, which is create this hierarchy of streams to overcome this limitation of the number of requests. Basically, you have a main stream, and then you have 4 second-level streams, and then for each one you can have up to 4 third-level streams, and then you can add more as you want. So in the end, you can consume from any of the streams, and you have to be sure that you are consuming only from the leaves, and you are limiting the number up to 4 for each one. But in the end, it's a kind of a nightmare to maintain, because you need to, increase the number of topics in the hierarchy and add more consumers, and you need to be sure that you are balancing all of them on every leaf. So this was discarded, but was a solution that was provided at the moment. Okay, so at some point we decided that we need to find a replacement, and basically we start analyzing options available in the market. The first one that we analyze is PubSub from GCP, from Google. Basically, it's a nice solution because it's a highly scalable, it's a proven solution, and performance-wise is working really fine. But we found some limitations on our side, which is basically it's a different cloud provider, because we have everything almost hosted on AWS. So adding a new cloud provider and integration between 2 clouds, it's a bit risky and hard to maintain at some point. And then the latency that you introduce in this cross-cloud communication is high also. Okay, then we move on with another option, which is the SQS plus SNS. Basically, SQS and SNS are services provided by AWS also. SQS it's a typical queue where you publish events on one side, and then you have one consumer which will be reading from this queue. If you compare this with Kinesis or Kafka, you have only one consumer. So if you connect multiple consumers, all of them will be reading different events. So you are not sending the same event to all the consumers. So it's not the same as Kafka or Kinesis. So in order to mimic this behavior, you need to use something along with SQS, which is SNS. SNS is a system to send notifications. So basically you create one queue, one input queue, and then with SNS, you send every message to an output queue. So if you have, for example, 3 consumers, you need to have one input queue and 3 output queues. And then with SNS, you send all the messages from the input to the output queues. And then the consumers will be reading only from the output queues. So this is something that can be done. It's not that hard because you can basically the consumers with your application. And also it's a managed solution because it's maintained by AWS. And it's working with our existing cloud provider. So it was a valid alternative. But the limitations or the cons are basically that you have to create this new queue or put something in place to create this queue for every consumer, which might be a bit of hassle depending on the amounts of consumers that you have to create or maintain in total for the company. And then there are also some limitations regarding the FIFO queues, because there are like two flavors. If you want to maintain ordering, you need to use these FIFO queues, and the FIFO is working with a certain limits. So you need to, if you need to produce more than that limit, you are not allowed basically. So it's a problem for us. So we discarded this option also. And then we move into Kafka and we analyze several options. One of them is MSK, which is the managed solution of Kafka provided by AWS. So we explore this option, but basically there is one, sorry. There is one major drawback for us, which is the knowledge required and the access to the system. Because in the end, if you are using MSK, you are using a Kafka automatically deployed by AWS on EC2, and then you don't have access to all the internal components. For example, if you're using a version of Kafka based on Zookeeper, you don't have access to, you have a limited access to the Zookeeper. So if there is any issue, all the troubleshooting goes through Amazon, and you need to basically open a ticket and then try to explain the problem, and it's a bit problematic sometimes. And also you need to have like some deep knowledge to troubleshoot these problems if you are not getting a solid response from that side. So in the end, we discard this option and we move with the last one, which is Confluent Cloud. This is it's a managed solution also that is that can be deployed in any cloud provider. Basically, you talk with them and you say, okay, I have my applications running on these regions, on these cloud providers, and I want to have the cluster running in this same region. So they will spin up the cluster there. Okay, so, and then something which is really nice basically is that this company was created by the actual creators of Kafka. So there are some people that created Kafka at the first place working there, and they are contributing a lot to the actual Apache Kafka solution. So you have all the benefits of the open source Kafka with the support of, or the enterprise support of this company. And the main drawback is it's a bit more expensive than the other solutions. We decide to go and move forward with this approach.
So we saw all the drawbacks of Kinesis. We make the decision to move to Kafka, but obviously we need to plan this. And one of the main drivers how we do it was developer experience. We have 500 plus engineers. We have more than 60 services. So trying to do this in a way that we make sure business is still, business continuity is okay without introducing bugs and without actually obsessing engineers. The other more important thing is the timing of migration. So we need to give the teams when to migrate. So Pablo gonna go what transparent to developers means, and we're gonna see also what minimal code changes and the timings around it. So the plan was, let's move as much as the producers to produce both on Kinesis and Kafka, move some of the consumers, or all of them, if we can, migrate the data pipelines, because obviously we have a lot of them, do the cleanup, we need to actually remove any reference of Kinesis and the code bases. Again, I said, we have microservices, we have a monolith, and all of Kinesis references all over the place. So we need to make sure also we do those cleanups. We need to make sure we remove the Kinesis, because we are paying, while doing this migration, we are paying for 2 providers. And at the end, obviously, we like to celebrate, and we didn't forget about that also. So all the plan already, I select go. Just to give a context, when we discuss about all of the configuration or some code base, our stack, so we are mainly JVM-based company. We have also Python as supported language, but most of the code you see are more for the Java world. And one of the main frameworks we use is Spring Boot. And when you hear us talking about JVM kits, we have a set of foundation libraries that we use in Glovo to simplify the building of microservices, which means like APIs or streaming. So we call them JVM kits. So, and most of the changes actually to migrate from Kinesis to Kafka was done in the JVM kit itself. I'll let Pablo continue to talk about the producer.
Yeah, so as you described, we at the beginning, when you want to migrate from one service or one system to another, it's usually wise to have both running at the same time for a while, and while you do the transition, and then you can validate if the migration is successful or not. So in this case, we decided to do the same, and the first thing to do basically was to publish the same events to both platforms. So the way to do it without disrupting too much the users, which are the developers in this case, was to modify some existing interfaces to publish events in Kinesis, and to add an extra interface to publish to Kafka, and then a third one to basically compose both. So at the beginning, we were sending all the events to Kinesis, and then in a best effort approach, we were sending the same events to Kafka. The main goal was to basically, in case of any events or problem or incident with Kafka, we wanted to have like Kinesis still working and silently fail, let's say, and move on in case of problems. So basically we did this replacement, and then we start producing for all the services in both platforms. So this was a rollout using feature toggles. Basically, we wanted to do slowly to see any potential problem that we didn't consider at the beginning. So for every topic that we use, we created a toggle to enable the secondary producer, which is in this case publishing to Kafka. So we went one by one, service by service, enabling topic by topic, and validating that we were sending the same data to both platforms.
So the transparent part is actually most of the migration to Kinesis to Kafka during the production part is totally handled by platform, because engineers, they don't have to care about it. So this was actually a smooth transition, and that was totally transparent to developers. On the consumer side, it's a little bit involved. So this was what we have. Again, we have annotation driven, just like Spring Boot. This is the way you register your subscribers to listen to some specific topics. You give them a consumer group, and the JVM kit will gonna make sure that it delivers this event to your subscriber. Minimal code changes. Before doing that, we replaced that one to Kinesis. It probably is one of our mistakes doing this, and we explain later why. So we didn't change any of the properties. We just changed the name of the annotation. So all the configuration and all the way it works was the same. Adding the Kafka one, it's as simple as actually adding another annotation. So it means now theoretically, this method will gonna be called from events coming from both Kinesis and Kafka. So now the problem is like now how we control this. This is where we talked about this control over migration timing. So we introduced the concept of consumption mode, which we can configure it through the feature toggle that has different states. And we defined active, pause, and discard. Active, as says the word itself, it means the subscriber or the listener are going to be called for that specific event. Pause means also all of these properties or like states are implemented for both Kinesis and Kafka, which means we can make active from consuming from Kinesis or active from Kafka. So it means like now we have two feature toggles controlling this. For pause, the same, which means like no, it doesn't consume from the stream. And this where the implementation is actually a little bit different because Kafka has the concept of pausing the consumer from reading from a topic. So it was an easy implementation, but for Kinesis, it is not the same. So it means like, we pull, but we don't do anything with it. So we don't commit the checkpoint. Discard, it's easy. It's like you read and you just discard, you like continue progressing. Control over the migration. So we make it a little bit granular to give again the proper timing for engineers or teams to migrate. The first one is by topic. The second one is by consumer group. So it means like by topic, we can activate consumption of that specific service to consume from Kafka or from Kinesis from that specific topic. Consumer group is for a group of consumers. We can do the same. We had one for the specific listeners, which actually should not be there in the first place because it has a bug, because it was impossible to implement it. And we never used it, or we used it like for a few days, but it was like disregarded. And seemed like pretty simple, like it's everything is implemented in the libraries. You push the libraries, you configure the feature toggles, and that's it. Now we migrated 60 services, 700 plus consumer groups, and pretty much 200 plus topics. And then like everyone said, like not great work. Yeah, there was like too much celebration there, but obviously that's not the whole truth. Challenges. So we did that, but it doesn't mean like it happened like in 2 days. And now we talk about all the lessons learned, the mistakes we made, and how we actually be able to fix them.
Okay, so I'm gonna describe these things that we faced during the migration. Like the first one is basically that it took longer than that we anticipated at the beginning, because it required some coordination with many teams to do some basically tasks to move from one platform to the other. And then we also faced some issues like with some dependencies and services which are working in a special way compared to the rest. So in the end, it took more time, and this is something that we faced. Then the second one is related to frustration. It's also basically because we require these tasks to be executed by the teams, and we need to do this planning and coordination with them. And basically, I think we could do better in this. We could have done better in this, like requiring less involvement from their side, and in order to speed up the process. So this is something that we also realized along the way where we do the migration, and it was basically too late to roll back and do it in a different way. And then the third one is related to the expectations and setbacks. We had some hiccups during the migration. We found some issues when we start rolling out like heavy producers and consumers, and then we had to like fall back and do some fixes on our side, and then start again rolling out. So this was also a bit of a problem. Basically, because we were like pushing teams to move forward this new platform, and then we had to fall back and wait a bit and then do it again. So it was kind of annoying for some teams or some people. So Yeah, I think I was also mentioning some of the things that are here. Among the root causes we have this also the insufficient knowledge sharing, because we kind of assume that people will be aware about the, similarities and difference between Kafka and Kinesis, which are pretty similar if you see from the outside. As I mentioned before, like these concepts of partitions and streams and topic is pretty similar, but in the end there are some nuances which are tricky to master or to handle, and then at some point we assume that everyone will be aware, and that was not the case. So we need also to, it's something that we should have improve a bit on this knowledge sharing. And then, well, this insufficient testing, it goes along with what I mentioned before, that these issues that we found during the rollout, and then we had to roll back and then regroup and do some modifications and try again. And the third one is basically more based on how to roll out this in a controlled way, because at some point we start rolling out some services, and when everything was more or less fine, we decided to move forward and allow all the teams to do rollouts at the same time. And this could be a bit messy if you are trying to basically do the rollout and verify that everything is working fine, and then you have issues that are appearing not because of the migration, but like normal stuff that usually happens when you are developing new features and new stuff in the application. So it's hard to know if you are introducing a bug or if the bug is related to something else. And then in the end, if you do this with one service at a time, is way easier than if you do it with 60 in parallel. So this is also something that we wanted to, we decided to do this in this approach to minimize the coexisting of both systems working at the same time, but it can be longer if you are trying to push and maybe too hard in this direction. So sometimes it's better to do it sequentially at the beginning, and then you have like enough confidence to move forward in parallel.
So now that we already migrated all of the JVM services, also the Python ones, we still have some of the data stream migrations, and I'm looking out to our data teams there. We are waiting for you. And obviously we still need to finish the cleanup process. Again, the cost is important for us, and we don't want to pay more than what we need to. So every time we actually finish the migration, we keep cleaning the Kinesis shards, plus also like removing the code. Good things, the lesson learned. I think the careful analysis of what to choose, and we are quite happy right now with Confluent Cloud. We had some hiccups at the beginning, but now we know how it works, and they add also like good features continuously. That was a good lesson learned. The zero code modification would have been done from the beginning, as you saw before. When we moved the consumers, we changed the interface, but we should have actually kept the interface and implemented dynamically if we have to consume from Kinesis and Kafka. Why I said that? Because the majority of the problems, like asking teams to go and change all of your subscribers and make sure that they are all working or they are in the decent state, it takes quite a long of time. And just not frustrated the engineers, but also frustrated our platform teams, because we need and you want to finish as quick as you can. And like, do not underestimate. Like we underestimated, I think the first success of the producers, which was like a smooth and clean. We underestimated the work that's involved doing the consumer side. We actually found in the middle of the consumer migration pretty difficult performance problems that actually pushed us to re-implement the majority of the code from scratch in less than a month. And one thing we are under also estimated, we try to stack all of the learnings that we have in Kinesis for the past 5 years in less than 6 months. So all the optimization we did in Kinesis, it's not just happened in one day. It happened during the last 5 years. And most configuration, we need to adapt them in Kafka also. So that's actually that simultaneous migration of all the entire teams, all the topics, created more headaches than actually solving the problem. So that was a good lesson learned for us to not repeat this again. That's all what we have, and we'll be here.
All right. Thank you, Gastón, Fanta, and Pablo. We can open the floor for some questions. Anybody? Yes, please.
Hi. What made you initially go with Kinesis instead of Kafka?
Pablo?
I think you might answer that question better than me because it was a decision made before I joined Glovo, so I cannot answer that.
What made you go with Kinesis over Kafka in the first place?
But actually, you might know, no? Like,
Is not for free, like as we said, like no, it took more than a year, the planning and implementation, and it means like no, it disrupts teams working on products and features. So we actually considered carefully if we have to migrate or not. I think at some point it was crucial to survive to migrate, but Kinesis worked until it didn't.
Hello, thanks for the talk. Have we learned something from this migration that we're going to apply, or we have changed already to the next one, that it's the Kubernetes one? Sorry.
Really want me to answer that? And obviously, I mean, I think one of the things we said about like obsessing teams and underestimating like teams have their own roadmap plan worked, and platform teams come and say like no, you have to do this by the next week. It didn't work well. So now for actually for the Kubernetes migration is well more planned, and it's also like if you want, do it yourself. The platform is going to help you, and we will not ask you or not put a time limit when to migrate. Even though like there are some migration, we need to put a time limit. Again, being on call for 2 different platforms and not knowing which one running which one, this at scale, it's also a problem. So there is a reason sometimes where we have to push to complete, but there are also cases where you can leave it to teams to take their time to do the migration. So we learned our lessons, and I think the Kubernetes one is going way more smoother than the Kafka one.
Okay, and just a second one. We spoke about the reason to change. How does it compare in terms of pricing, Kinesis with the new Kafka?
We cannot disclose how much we are spending, but we are definitely spending less.
Nice.
And also this is, I think it was part of also the planning, no? I think cost, it's, I think pretty much in all the companies is a key factor on decisions, and we knew that. So actually some of the implementation we did in the JVM kit and the library, we're conscious how to make, like, for example, less requests to the cluster to minimize costs. So we make sure it was like baked in the code base, also to add more alerts and monitoring. So today we actually were like pretty much every day we look the cost, because now we put a limited, we want to spend this much per month for Kafka. And right now we are using it for the past, I think fully for data in the last 3 months, and we have always been way less than we expected to pay.
All right, thanks.
You commented that during the migration, you were using feature tools in order to control the implementation of the interface of the producers, and also on a consumer basis. Who was in charge of switching these tools, and how it was the communication between the responsible of switching the toggle and the ones that assume the consequences of that switch?
So most of the subscribers or listeners, they're owned by a team. So all of that, I mean, there are the cases where at the beginning we are migrating, like platform was communicating, we'll do this work, but the 99% of the time is on the teams to make these changes.
We did all the production in platform. We enabled all the dual production and actually verify that everything was working fine. And then when we asked teams to move the consumers, they were responsible for switching and monitoring, basically to flipping the toggles and monitoring the
So you were responsible for the production part, and then once you ensured that the data would be like consumable, you gave them the responsibility to toggle their own consumers.
Yes.
Why is the Kafka solution cheaper than the previous Kinesis one? Is it because you don't need the specialized topics downstream, or are there other aspects to that? It also mentioned that it was the priciest. So would all of the options being cheaper than Kinesis?
Not all of them, but I mean, the billing schema is different for Confluent compared to Kinesis. And also in some cases, you have to do some things. For example, you need to add more shards in Kinesis to scale out, to have like, I don't know, lambdas, for example, processing in parallel or stuff like that. And you have to pay for every shard, while in Kafka, you can maybe do it adding partitions which are not charged in the current model. We have a limit of partitions included in the plan that we can use. So in Kinesis, for example, you need to pay each one of them, and in Kafka you have a certain limit of partitions included in the plan. So that's one, for example, one example of something that modifies the price that we pay.
Yeah, basically, I'm curious about what system do you use to enable the developers or the teams to configure their own topics, like setting the compaction or retention, things like this, or even create topics.
We use basically Terraform. There is a Terraform provider implemented by Confluent. We define all the topics, ACLs, all the configuration around that in Terraform, and the developers can actually modify that and create their own topics and modify the access for the services.
And in terms of architecture, did you design with more than one cluster for Kafka, or you have one cluster with all the topics and brokers there?
No, we are using, initially we are using only one cluster, because we are, I mean, with the limits of the amount of information that we are transferring, we are okay using one cluster. Actually, we use also one cluster for staging, but it's a different type. Basically, we use a dedicated cluster for production, which is it's a cluster deploy in the same region that we operate. And then for staging, we use a multi-tenant cluster, which is shared Confluent clients. But for now, we are using only one cluster.
Thank you.
So to finish on that one, there was a discussion sometimes to data to actually have separate clusters for data and using the linking feature from Kafka Connect. But it's something that we, at some point, for whatever reason, to protect the main cluster from others to use. But right now, yeah, we are running everything in one cluster.
regarding the MSK pricing, that you say that it was a little bit cheaper than Confluent. It was just a misestimation based on your knowledge of Kinesis and the kind of pricing that Amazon offers with Kinesis versus MSK, or it was just like with Kafka you can make better use of the resources and it's cheaper at the end.
It was a bit cheaper comparing to another Kafka solutions. So we were comparing in that case Confluent with MSK, and also we contemplated the option of like hosting or have a self-hosted cluster. But
because from the Kinesis point of view, always MSK seems like a lot more expensive in terms of throughput and well, the basic metrics. When you compare one to another, it looks like if you move to Kinesis to MSK, unless you have your architecture made specifically on Kafka, they are trying to push you to Kinesis just in terms of pricing. So it was surprising that Confluent was initially a little bit more expensive, but it was eventually cheaper, mainly because of the way that they are charging you. I don't know exactly how does it charge Confluent. I don't know if you are just paying for the resources and their cloud, and then you make the better use of that instead of the pay by use that Amazon provides.
in the end, it was cheaper than Kinesis. But if you compare, I mean, all the pricing models are different. In Kinesis, you don't pay, for example, for the amount of data that you transfer, but you are paying the concept of something called shard hour, which is including basically this, because there are some limits. You can produce up to, I think it's 1 megabyte per second, and you can consume up to 2 megabytes. So they, in the end, they know the worst case scenario, and they charge you for that amount. So it depends on the use case. For example, if you need to scale out a lot and use many partitions because of your use case, in Kinesis you pay a lot. In Confluent you don't pay that much because it's included in the bill already. So they are not interchangeable, the costs. But in our case, the way that we use it is cheaper Confluent than Kinesis. And the analysis that we did with MSK, based on the information that we had at the moment, it was Confluent was a bit more expensive than MSK in that case.
Thank you.
I have one question, if I can.
Yeah, go ahead, please.
Yeah, so you mentioned that like there were some limitations in the Kinesis, like 5 transactions per second, and you have to wait. We have to like design our solutions around that limitation. Is there any limitation in Kafka as such, or like did we hit some blockers in terms of limitations with regard to Kafka?
No, I mean, the way that it works is different. There are obviously some limits to protect the cluster, but the values are way higher. So basically you can have multiple consumers, and then all the consumers are basically talking with the cluster, sending different messages. It could be fetching, committing, and there are obviously some limits on the amount of operations that you can do per second. And the Confluent in this case is enforcing these limits to protect the cluster. But the values are at cluster level, so you are not compromising one consumer with these limits. And also there is a possibility to set quotas per service. So you are also you'll be able to, I mean, protect the cluster from some services that could be misbehaving and sending more traffic than is expected. So in the end, there are always limits, but they are way higher than the Kinesis ones.
Right. Maybe a further extension to that is like, do we understand like why Kinesis has this limitation? Is there like, as you mentioned, like there are some limitations in Kafka to protect the cluster. The 5 transactions per second limit on Kinesis, is this something to protect, or maybe the technology bound, or what is it?
We had actually a call with the service team from Kinesis, and we exposed this information. Actually, we asked if it was possible to raise the limit, because in the end, we weren't consuming that much information. We just were like polling frequently, but the amount of information transfer was not so much. but they did say that this is a limit by design. But basically, all the limits around AWS are to protect the system, because in the end, you cannot, I mean, the system shouldn't crash at any moment. So the only way to protect it is to define these limits. Yeah, but I think Kinesis was not designed to be used in that way. It is heavily used inside AWS. Like, for example, I think all the CloudWatch metrics and everything is processed using Kinesis. So it's a really powerful service, but I think it was created for this streaming application where you have up to, I don't know, 4 or 5 consumers and not more than that, which is not our case.
Makes sense. Great. Thank you.
Welcome.
Ismail, please go ahead.
Hi, glad to see Gastón here. Welcome. I have 2 quick questions. One to Gastón about the cap. When you had the eventual consistency, what were the biggest challenges with that, beside from latency, of course, and having something that's delayed? The other question for Pablo or Fanta about the consistency between the events. We have 2 sources of truth there when we had the Kinesis and Kafka. So how did you keep up making sure that these are both synced and no issues happening there, or were there any issues actually? Thanks, that's all.
Okay, for the first question, how do you deal with the eventual consistency? It depends on the system. If you are trying to have like a read after write when we have an eventual consistency, and you write and then you read from the system and you want to use that read to do a transaction, a bank account, you are going to have a really hard time. But in feature toggles, it's way easier because we are just reading the configuration over and over and over. And it's a matter of seconds, maybe a minute if there is some hiccup with the network, that you get the latest update. So we are not speaking about, eventually next day you will get the data. No, it's a matter of seconds. And for this type of system where you are just refreshing, it's kind of a snapshot of the data. It makes sense. Again, depends on the use case. And I hope that answers your question.
Yeah, thank you.
Okay, so regarding consistency, just to give you some context, that at the beginning it was like a kind of a sense of low confidence with Kinesis, and I think Gastón can prove that. But because I don't want to, explain too deep, because we could do another talk about that. But Kinesis work in a different way to produce events. Instead of like talking directly to the Kinesis backend, you have something in the middle running in the same instance, which is another process, which is called KPL daemon. So all the messages that we are sending to Kinesis are going first to this process, and then this process is relying that to the backend. So sometimes this process might crash, and your application is still running, so you lose some events in that scenario. So we had these scenarios like many times, and so the confidence level was low with the production of the events. So you produce an event, but you are not sure if it reached that point. So when we added Kafka, it happened that Kafka was more reliable than Kinesis. So all the events were reaching Kafka, but not the Kinesis ones. So we had these issues of, I have my events in this platform and not in this one. So we ended up creating a small application service, which was enabled per topic to compare. So basically we created one for some topics, we created one consumer in Kinesis, one in Kafka, and in a 5-minute window, we were consuming events and matching by key if the events were in one platform or the other, and then publishing this with some metrics to a dashboard. So basically we use that tool to answer all the questions that we receive. My events are here or not. So we were basically had this running and comparing the events. Yeah, in some cases, like when the daemon was crashing in some scenarios, we saw that the difference was on the Kafka side. We had more events. But then along with while we're doing this migration, we were fixing lots of issues with Kinesis because we had to maintain both platforms, and we managed to keep it more or less stable at the end of the migration. So I think this tool was used for this purpose, and actually was like decommissioned recently. So it's and the name is yes, KK.
Please, Albert, go ahead.
Hey folks, thanks for the presentation. Question on Kafka migration. I believe for Kinesis, we had some sort of solution to keep track of where each consumer was within a stream. I believe that was using DynamoDB internally. Maybe. Have we gotten rid of that as well, or are we still using it?
Are you talking about to keep track of the offset while we are consuming? Or?
I think so. It is to know, like, it's a cursor for each shard, like where each consumer is within a shard.
Yeah, the way that works in Kinesis is you have most of the heavy stuff is on the client side. So all this negotiation to see who is going to consume from each shard and stuff like that is defined using something in between, which is in this case a DynamoDB table. So basically this table is to use to coordinate all the clients and assign the partitions or the shards to the clients, and also to store the checkpointing information. In Kafka, this is stored in the server side in a topic, basically a topic that contains all the offsets. So whenever you are finished processing an event, you send this commit message with the offset. So basically you are acknowledging that you already processed that, and this information is stored in the server side. So it's not anymore on a separate entity like this table.
Cool, thanks.
Hey, so okay, when you were talking about the unleash way of doing the caching for the feature toggles, so if you cache the info from the feature toggles database locally, no, so they can compute whenever the database is down. If you do that at the application level, or like at the whatever application container level, how do you bring up new container application containers whenever that happens? No, if the external server is down, the ones that are already that data cached, that they work. But like if you need to do a rollout or something and you need to bring up new servers, how does that work?
You are speaking of the servers on the client side.
Yes.
If you are deploying like a proxy.
Like your application uses Unleash library, no, and it caches the things locally to not have to go to the Unleash server all the time. So whenever you bring more of your own servers up, what happens?
You can define how it should behave. So we had an implementation of the proxy that will just default. You always have a default for every value of the feature toggle. So probably if it's a release toggle, the default will be false. If it is a kill switch, it might be true. It might be false, okay? And when you kill the feature. This is configurable.
And where do you define it?
You can define it in the configuration of the SDK. When you spin up, you have also config of this proxy, and you can define this behavior. But it's not ideal, because in this scenario you will end up with all your old behavior in your application. The new thing that we are building, it was released last week. We also provide an external storage, external and persistent storage. It can be S3, can be Redis, can be anything. We now have S3 and Redis. And the idea is that whenever you pull data, you can put it into this persistent storage, and then you can try to read from the upstream server, and if it fails, then you go to this storage. It will have some kind of stale data, but still it will be better than just falling back to everything is off. We are still trying it out. So, thank you.
Thank you.
All right. We have time for one more if anyone wants to go.
just for people to kill me before the pizza. It's for the only one. So yeah, ideally feature flags are true or false, but I have seen in the wild people using it more like a key value store. Like this feature flag will have this value, that, or another one, or a combination, pretty much like key value. Do you see this in the wild, and do you have like personal feelings that is a bad practice?
No, it's not a bad practice. Actually, I just explained what a feature toggle is in the basic usage, but you can have like payloads, and List supports like JSON payloads. You can add strings, numbers, whatever. And I think the feature toggle solution that Glovo uses, it's a different one, homegrown, and it also has that kind of usages. And it's useful. It's up to the client what they do. I think 99% of the cases, or well, let's go 70-30. 70% of the times you will need some additional information. Like, I don't know, you can store some configuration, like the color of the button that you are showing. You put it into the toggle configuration, so you can change it. You can have multiple values. It's not just like a Boolean store. I don't think it's bad practice. I think all the feature toggle systems out there support this in one way or another. So yeah, I don't know if it answers the question. I don't think it's bad. It's something that it's built in. This was just a basic example.
Okay, thank you.
Okay, and now I can call it for pizza.
All right.